Okay, so let's on my lecture end, I got the impression that perhaps this the derivation of the equation and the solution in the boundary layer was not fully understood. So I think that it was to very briefly, to remind how it works, and after that we also will consider in the detail the task, which allow us to better to understand. So I am somehow return to the equation 3.8, which is shown here. I will show just in PowerPoint presentation. And the extrophic flow obtained in the previous chapter 2 will obviously satisfy equation 7, from which the derivative with respect to the sketched variable theta is completely eliminated. Therefore, we represent the flow velocity in equation 7 through the regular or phasic geostrophic part and the singular or boundary part in the form. Let me explain how this thing is working. Oh, I don't see. Okay, so first of all, on the radial direction, we are taking into account theta component and psi component, and we also considered axisymmetrical situation when there is no dependence on phi. So actually it allows us to simplify further this approximation. And also there is only two components of the flow. One of them is which is directed in the direction of theta function, and other is which is directed in the azimuthal function direction. This is actually due to the fact that we have almost no contribution in the radial direction. So there is no contribution in the radial direction. But here we have a very clear phi contribution, which is in the azimuthal direction. And this contribution constitutes two parts. One part is the regular geostrophic flow, which we could reach. This one I show the mouse. This is the regular geostrophic flow, which we should reach when we are outside the boundary layer. And this is another, so it's in some sense supposed to be known. And here we have another part which we will be calculating dependence on, to which our flow will be under condition that its geostrophical part is completely absent, and in excess that there is corresponding boundary condition are satisfied here. So we have only two components in theta direction and in phi direction. There is no component in r direction, but more precisely to say, there are some components in r direction, in fact, but it's singular component. It's working only in the boundary layer, and working maybe possible to say somehow sharply, very sharply, this zeta is working. How it's working, let's see on another slide. So to obtain the equation determining the singular velocity from 8, it is sufficient to consider both angular component of the vector equation from 7 and 1, taking into account the geostrophic equation 2.8 and 2.14, and the fact that the angular part of the singular pressure gradient is negligible. As a result, we obtain. So actually, again, I stress this simple result appear only because for the Coriolis force, we have no component. For the Coriolis force, we have component only at the geostrophic flow and also at the Coriolis force. And from the geostrophic flow, there is also no component here, but there is a component which depends on this theta things, which is doing very sharply. And this one, again, also the same. So we have the component of the velocity which we obtained from the previous equation. And here there is a very simple equation. We can solve it with the boundary condition. Boundary condition is that theta component is not at the boundary of the outer boundary. Here there is very specific boundary condition. If you remember, we this term specify in this way. So it at the boundary, this complete term, small u plus capital U, should be equal 0, or otherwise it's there is a sort of the cancellation of the geostrophic flow U directly on this boundary at R equals C. And also there is at the same boundary, at another boundary, it's at one boundary, and if we consider another boundary, here we have a little bit another situation. At least in C component it's the same actually, this situation, but on this component here we have again this effect of the geostrophic flow, but also there are some differential rotation, and we can understand this boundary condition by just rearranging this capital U to this side. Then we have the sum of the small u and capital U, and it's exactly what we assume in the initial flow. You see that here there is a U, small u and capital U. So we are setting out this boundary condition, and the problem is quite simple actually, because it's this the ordinary linear equation in respect of theta, in respect of xi, sorry, in respect of xi. So this xi is quite ordinary, and we can use it like that. So for it's sort of the classic things for this condition that this small u, which we are looking for, and this component, theta component of the velocity, are all proportional to the exponent of some eigenvalue lambda times this z component. And so actually eventually we have this representation, whereas there is a component which depend on the could depend, actually not depend, but could depend on the various value of lambda. And so also there is the exponential part, and this xi component. I just remind you that this xi is actually the ratio of the difference between the actual r from the boundary, so it's actually small value, and you divide is by the square root from the Ekman number, which is also small value. So these small value are both compensated in the boundary layer, but if we are going outside the boundary layer, then we actually have that outside the boundary layer, this work in the opposite direction. It's not compensated, but it becomes to diminish. Of course, to reach so, we should impose the proper lambda coefficient, and to find it what is it working for and what is it given for us. So actually, then we are resolving the characteristic equation. In this characteristic equation takes the form, and it's important to know that at the moment this theta, we are not resolving against this theta component. It's play while it's coordinate, but it's not playing the role because there is no derivatives in theta, and so it's plays sort of the parameter. So we just can regard this system like the system with the parameter theta. So we eventually, because the derivatives are only in respect to the radial derivatives, which effectively stretch it out, that it's concentrated near in the boundary layer. And the same situation is for the with the second equation of this type. So eventually, it's obviously that from these two equations, we have characteristic equation, which is written here like that. So, and it's a fourth order equation, as you can see. Therefore, we can, an alternative approach to find a solution to equation 9 is to exclude the singular differential rotation u from it, and then we immediately obtain a single equation. So this we obtain this single equation. So previously we just solved two equations, each of them of second order. But there is also a more simple way, maybe which we choose, that we are putting one equation into another equation, and so eventually we are getting fourth order equation. And this fourth order equation, of course, has a solution with characteristic equation which look like that and determine this lambda stuff. And it has two sign, plus minus sign and plus minus sign. So for finally it constitutes four solution, and for different full number. So we are very much could involved in this stuff, and so eventually, finally, the solution for latitudinal component of singular flow can be written in this form. And you see that just in one form we merge together the boundary layer which is outside and the boundary layer which is inside. But the chosen this lambda coefficient we put here for the real part, of course, of all this situation, because there is an imaginary part, but we don't interested by the imaginal part, but we are working only with the real part. This real part, you see that there is a plus here, and with this plus sign, how we define this xi, O. This xi O allow us to diminish this term, all this term, when we are well outside from the boundary layer, just because this is exponential dependence, and it's divided by the small e number, and so if we are going sufficiently away, even not so much sufficiently, we can, for example, move just 1.10, less than 1%, and it's already more bigger terms come and forth, and they will produce a diminishing of this structure which is inherited from the boundary. And the same play is here, but I should stress that here there is minus sign, just because this component of the stretched variable was defined in the same way as here, but if from this outer layer we are going outside the layer, we should go in the direction of the smaller r. But here, to go outside from the boundary layer, we should go in the direction of the larger r, because this is the inner boundary. So from the inner boundary, we should go up with rising of the r. And while here we should go with diminishing of the r. So if we go from the outer boundary, then we go this way. So eventually it appears that there is a different sign, and it's possible to do because we have even 4 different signs. So this combination of two will show the overall. So here you see that in this way we can get the formal representation. And also it's interesting to stress that this formal representation is dependent on some sort of the free function which are here written. There is 2 free functions which we will use further to satisfy the shear layer condition. And but anyhow it will satisfy to the boundary condition. And because it's one unique equation for the v theta, but for the another component which is actually working in the phi direction, azimuthal direction, we should just take the second derivatives of the theta and we get the exact equation for the this phi component. Azimuthal component otherwise. Or maybe more precisely to say that it is not complete of azimuthal component, but this is just excess over the geostrophic flow. Because as I showed you in the previous slide, we have this representation. There is geostrophic flow and there is this function we are looking for. And so eventually this function is working in the way that it's cancel the geostrophic flow on the boundary, while this function itself removed from the boundary layer structure, and we have only geostrophic flow outside the boundary layer. So in this sense, we are perfectly matching the boundary layer and geostrophic flow. Okay, so it seems I repeat, I hope that maybe this point is a little bit better clear. But to the next part of this lecture, to proceed to the next part of this lecture, I think that it will be good to name you some task which is possible. Okay, maybe now I should set another PDF file, sorry. I'll do that. This one 17. This one 18. Oh no, there is no. Okay, so unfortunately there is no presentation about this task, so I will write down here about this task. Okay, but for the reference we should keep this equation, to which we will return in some place, at least this one, and then we see what else. So actually we are close this chapter, but nevertheless there are some important tasks which some of them we explain in the detail, and another of them you just please write down. I dictate to you and you just write down for you. So exercises for chapter 3. 3.4.1 task. So please write down. Carry out in detail all the transformations necessary to obtain the scalar system 1 from the vector equation 0. You remember that it was the equation 0 from which we started this chapter, and after that it was equation 1. So your task is carry out in detail all the transformation necessary to obtain the scalar system 1 from the equation 0. So there is some example how to do so you can just also write it down. For example, the radial component of the Coriolis force is found by multiplying it by the unit vector grad r, or otherwise yeah, sure. I'll show that. Okay, so for example, the radial found by multiplying it by the unit vector gradient R. So we are doing such an operation. For example, 2v multiplied it by grad z. And then we want to get the radial component of this. So there is the vector multiplier of the here. To get the radial component, we simply scalarly multiply over the grad R. So then we could proceed like this way. Now I'm only speaking about radial component of the Coriolis force. So you know that there is a dot value and the cross value with the vector quantities, and you can exchange them. It's a very important rule which is very often used, and in this situation it's quite usable to exchange these two, and it's change nothing. This is, I don't know how this rule name in English, but in Russia we say that we can exchange dot and cross, something like that. So actually, to get the corresponding value of the radial component of the Coriolis force, you are working like that. You keep this and you put dot here. So consequently, you have grad z multiplied by grad r here, and dot is here. Just to make it absolutely clear, let's do like that. So then we just expand this vector product on the corresponding gradient and multiply them. So we have 2v vector, which is, okay, let's, for definition, make more brackets. And so from this one part, you know that the z is r cosine theta. You know that. It's just by definition. So we, after acting gradient on r cosine theta, we obviously obtain cosine theta gradient r. Then here with positive sign, we take the gradient. Gradient is just cosine theta of this value. And so, and it's also multiplied by the unit vector in the radial direction. Then we take the gradient of the cosine theta, which is again the theta. So it will be minus sine theta. So it would be minus sine theta, and here we have, and here we should have this next part of the unit vector, and here it could be written like r grad theta. This is all this is unit vector. Okay, so finally we should just multiply by grad r, which we keep from here. So eventually, after all the identical transformation, which we have here, this stuff is cancelled, this stuff will remain, and so eventually, I will maybe even write here on the top the final result. So we How for radial component sinus theta v phi. So, and this in the same fashion we can expand Coriolis term in the same manner like we did here. Then let's. So, should I remember? Do you understand this task one? Is it clear? Okay, thank you. So then let's I formulate for you the task 2. Prove that the radial component of the velocity is negligible compared to the angular components of the velocity in system 1. This is a thing that which you use in many times, but you'll better prove it somehow. Also prove, this is the end of the first sentences, then related task, everything is here. Also prove that the pressure in equation 11, following from the angular component of 1 and the first equation in 7 also can be neglected. So let's give you some instruction how to better to make this proof. Just again write down for proofs. Use the incompressibility condition 2. Incompressibility condition is just divergency of V is equal naught. The radial boundary condition from 3. From 3. And the necessary asymptotic consideration presented in this chapter. Okay, this is not so difficult task, I hope so, and you can solve them. But the third task I will give you by myself in detail. Okay, let's remove that. Okay, let's again write down this, the formulation of the task, then I will present you a solution. So this is the third task, so its number is 3.4.3. Let me say you formulation of the task. Express from the first radial equation of system 1 or 7, actually system 1 or system 7, they are almost actually in our case equivalent. Expressed from the first radial equation of system 1 or 7 and from the second equation 214, this 214 is from the previous chapter. So 2 is the number of the chapter. 2.14. The pressure P is pressure P and its gradient in the boundary layers and in the main volume as the functional as a functional of the functions So we as of the function us for geostrophic flow, and this free function. Maybe you remember them. That function were introduced in section 3.3 and 2. Actually from all the previous equation we saw, when some of them are here. Okay, let's now to try to find the solution. Okay, we express, so the situation is, if you follow my step, you see that I express the different component of the velocity, but for the moment I forget about pressure. It's partly because this pressure was somehow from the leading order is removed. Only a radial component of the pressure appears, but this radial component is not important for us in estimation of the velocity. But nevertheless, some pressure appears. So we, to find this pressure, we in some sense should go in the next order of this approximation. So we express pressure through the geostrophic differential rotation from 215 and the additional pressure delta Q. Okay, so we suppose that there is some additional pressure delta Q. There is some additional delta Q in the Ekman-Bandelier layer. And this additional pressure should work like that. Because, of course, there is some geostrophic pressure which related to the gradient of the P. And to get the P itself, not the pressure, so we should take the integral from 0 to S, where S is cylindrical radius of U S ds, of course, and this addition of this, maybe it's better to say shear layer. So it's constitute delta, which is e to the half of the delta, which is e to the half of the Ekman number related. You know that because you're already accustomed with that. And then also there is some Q, which is additional pressure. And here, why we use this delta? Because if we take the radial gradient of this Q, then we have effectively we divide on this delta. So these two delta are cancelled, and so this is contribution in the boundary layer becomes of order 1. This is the trick. And this Q is, of course, like this free function and everything we showed before on this. It's impossible to see, I don't know. So what happens? It's clear on the screen? I don't know. Oh, it's okay. Yeah. Thank you. Okay, thank you. So based on the previous, okay, I didn't finish it. So this contain dependence of theta over xi, of course different in the different boundary layer, and also this p is actually depend only on in the major part on s, but in the boundary layer it's mainly depend on the singular variable and theta. So we should estimate this integral. Based on the previous problem, we write the radial component of equation 1 and the corresponding solution for the change in the pressure gradient in the Ekman layer as I already told you, if we take the radial component, effectively we not take the radial component, but we take the stretched component, this one. And it effectively removes this delta. So eventually we have this equation for this addition to the pressure, which is Q. dQ by dxc minus 2 sine theta u. Actually, this is equal not, but maybe I will write short like that. It will be the same. And the second equation is actually the constitute this integral. And we can write down that the Q from another point of view is sine theta so just follow from this. Maybe better to show such an arrow because it's following. Okay, I can also use the comma. So 2 sine theta u integral u dxc. This integral of course in xc. So the last integral is expressed in outer index O at the top and inner index I at the bottom layer as. There is actually rather a bit lengthy formula, but I try to fit it. Okay, so we can express, there is different expression for the different position. So we can express like that. Okay, on the top we will have the outer boundary representation. On the bottom we have inner boundary representation. So we take here Q naught from theta minus 2 sine theta egret naught from theta and also we have this integral, and because this integral for the stretched variable, we take the stretched variable at the outer point as a limit. But we can, as far as I already told you, if we go from the outer boundary to the inner boundary, so we are going down in sense of the radial. But it's not exactly the radial, it's actually a radial value divided by this very small theta. So it becomes very big value, and it could come even up to minus infinity, and it's negative because it's diminish all the stuff exponentially. So here, to make sort of the exact correspondence that all this stuff is vanishing, we should put the minus infinity. And here we have the real part. Of this, another part of the resulted exponent square root cosine theta e plus 1 theta okay, here the real part of this and this integral over deck C. And for the we have the similar quite similar stuff for the inner boundary. Some arbitrary function QE minus again 2 sine theta y theta. And here we have another integral, because I already told you if we go in outside from the inner layer, we are going in the direction of the rising radial derivative, radial stuff. And because it is stretched, actually it's extended up to infinity. And eventually all this stuff are vanishing. Again, real part. We are taking the real part. But here there is some small difference. Exponent square root of cosine theta. And here we have I plus 1. Oh, sorry, we have plus 1 on the top, but on the bottom it's minus. Just to satisfy all the conditions. And this is another C, and we take dx C. Okay, so we can precisely calculate these two integrals, and the result is, maybe I will not rewrite this all the stuff. I just simply show. Show the results. I will take the result that all this integral, you just can write separately. Let's just to represent this integral. Of course, the initial values are the same. So we see that this integral is equal, finally. Of course, the multiplier is the same, minus 2 sine theta and free function y0 from R from theta again, yeah. And we have not integral, but the real part of this resulting expression. Here there is the cosine theta. E plus 1 theta O, and here there is the denominator, which quite clearly also has the same structure but slightly different. Here we have square root of cosine theta again. Here I plus 1. The only difference is that here we have under the exponent and here under such a situation when we integrate that. So we are finding integral and show it this way. Oh, maybe I was wrong to write down this. I reproduced it all with the produce it all this stuff. But let's reduce our problem for the lower part and reproduce only the integral, which we constitute the final solution. And this only integral is the real part again. Of the E square root of cosine theta and in this case I minus 1. I is this imaginary unit, you know. And of course the below things is also quite similar, quite symmetrical. Cosine theta I minus 1. So this constitutes the final solution. Okay, it's a bit tricky formula, but nevertheless it's in some sense exact formula. So here expression 315 is used, and R correspond R, this re value correspond to the taking the real part of a complex number. And finally, if we combine all this stuff together, the required expressions for the pressure gradient. Let's write it down and it will be the final. If you are interested in some intermediate step, of course you can do that by yourself, but here it seems I have no time for that. But let's just write down the final result. Okay, we will keep just this result for this integral. One and second one, just for the reference. And the final result is, first of all, to represent gradient P. So it will be 2U capital from S, grad S. So it's obviously because it depends only on cylindrical radius, so it depends on the gradient S. Then we have next contribution. which come from the outer layer, and it's no wonder that this pressure has only geostrophic component, which is of order 1, and so it's keeping to be important. And also the next component is purely radial component, and it's constitute, of course, 2 component. It's look like that. And it's constitute the free function y, but which we defined it with you before. Just minus if we open all this real value and to get the final result. So we have this uy function and exponent cosine theta cy, and it's multiplied by cosine from the square root of the cosine theta, so rather tricky estimation ci, and then minus, let's go here. So this is contribution from the geostrophic flow, this contribution from the inner boundary, and the next contribution is obviously from the outer boundary, YO. Of course, these 2 functions are dependent on theta. Again, we have epsilon and another sign, as I already told to you. And then again, cosine square root from the cosine theta C naught, CO, sorry. So we close square brackets, and as already told to you, this sort of singularity contribution in outer layer and inner layer, inner layer and outer layer in this order. So here there is only radial component, grad R. Okay, so it's finished this problem solution. And this actually solution we later use for estimation of the shear layer and everything to completely complete the task. Okay, it seems that it's time for the question. Please raise your question. Yeah. This geophysical, you mean geophysical flow? Yeah, this is coming from the very first thing which we started, geostrophic, no precisely geostrophic flow, not geophysics, just geostrophic flow. Yeah, so this geostrophic flow is coming out from the general solution. But to find it precisely, we should accommodate not only the Ekman boundary layer. At the moment, we just via some not known yet geophysical, just perfect flow. But when we proceed to the shear layer and other layer, which finally formulate the flow, which finally formulate the flow. So then we define precisely what will be the geostrophic flow. And it will be, as I already told you, this geostrophic flow will be, when we apply all these conditions, it will be the first step, sort of the first order approximation. So at this first order approximation, we precisely determine just from the boundary condition and from the shear layer condition. Then we determine that this geostrophic flow is rather simple. As I already told you, there is a rigid body rotation outside the tangent cylinder, and also it will be some change inside the tangent cylinder, but quite smooth change. So there is only jump on the tangent cylinder itself. On tangent cylinder, there is a shear layer, which is responsible for this final picture. Yeah, so eventually we define it precisely. Of course, it will work in the case, in any case, because we are considering only specific case, and there is a differential rotation. Nothing. There is no bind support. There is nothing. If we are combining it, but in this case, when there is only differential rotation, at the moment we keep the general. But later, in the next chapter, we will go to the precise form, which is namely for our task. Is there any more questions? Yes. Yes. It's a little bit of delta. It's gradient. Okay, we speak almost about 1 hour. Thank you very much for your Professor Rani, since that it's over, you can stop. Or maybe you have to your place.
Your task. It was what you have to do. And we will share also. Don't worry. We want to show it first. After that, you just open a break and think we have 7:30 is the cultural program. Today I posted now. Games.
So task 1 here, the formulas 0 and 1 are mentioned. Yeah. So let's do it like this. Here is task 1. Yeah. We can make a photo or something, and let's check what we've got as system. Thank you. System 0 and 1 here in our list, and compare it with your notes also. So 0, it's just a definition of viscosity, this one. Yeah. And 1, it's shear stresses in the forms of vector. So that's about first task. So we can even, so what we can do, we can check, you've got your shared lectures, yeah? First 10 lectures, yeah? So also let's check the numeration. No, it's here. Lecture 2, it should be. Yeah, so this formula and so first 2 slides of lecture 2 you need for this task. And for the second task of chapter 1, yeah, repeat. For the second task, here we need formulas 13, 12, 14, and 15. So let's check what we've got in this case. Yeah, it's just a definition of total velocity in the rotating system. Navier-Stokes equation, and modified pressure. So that's all. So that's all with chapter 1, and going to chapter 2. This geostrophic flow and all this stuff. We've got these 2 tasks also. Here just the text of this task. First one, perform Taylor transformation to obtain the dimensionless system 5 from the dimensional equation 0 and 1, provided that variables are transformed in accordance with 3. So let's check how it looks like. So we need 0, 1, 5, and 3, all in term. 0 and 1, it's our initial set of equations and boundary conditions. System 5, here it's just dimensionless system. So Rossby number and Ekman number appears. Why they appear here? Because we used this set of scaling. And also, let's take a look at what this lecture, I guess, supposed to be this one. No, sorry. Guess this one. Yeah, it's lecture 8. So these formulas 0 and 0, 1 in lecture 8, and in the next lecture, lecture 9, we've got non-dimensional system 5. I hope. So yeah. So this is the scaling. And this is our non-dimensional system 5. So that was task 2. And last lectures, they are not shared with you yet, but I guess in an hour they will be shared. So let's also check the tasks for chapter 3. Chapter 3, and Rossby number and small Ekman numbers and layers. So the first task is quite simple. Yeah, we just want to rewrite vector equation 0 in the form of system of scalar equations in spherical coordinates. So let's take a look at these equations. So this is the initial equation, equation 0, vector equation. And then we just accurately rewriting it in the form of free scalar equations as a spherical system because of this vector Laplacian here. We've got not very nice system nevertheless. So that was the first task. And the second one, where is the second one? Yeah, second one. Prove that the radial component of velocity is negligible compared to the angular components of velocity in system 1. So it's just scaling. You're working with very thin layers. You know that radial derivatives were huge, and you need to balance the terms in the equation to be of the same order. That's how you may receive and prove these results, that some components of velocity are huge, some are not. So what equations are needed here from your last lecture? 11, 7, and initial one, 11 and 7. 11th equation, yeah, it's this dispersion relation lambda, and 7. Where is our 7? 7, yeah, again, it's initial equation, but for the stretched variables inside the thin layers. Okay, so these lectures, these last 3 lectures, and it's chapter 3. Yeah, will be shared. So these 2 tasks, yeah, you can also do. And the last one, this task, yeah, it's still here on the board, expressed from the first radial equation, from the second equation, the pressure and gradient as and its gradient in the boundary layers. So yeah, it was done recently, so you know the solution. You don't have to do this one. Okay, so that's all. So for all in all, first 2 tasks were kind of solved. So you've got 1, 2, 3, 4 tasks, yeah, to be completed. Yeah, if you want to feel these equations, you need to do it. Okay. Oh yeah, that's all. You can stop. And of course, yeah, if you've got any questions, you know, we've got group chat, yeah, so you may right there, you may ask now. All possible means you can use.
Start the next one. It's next week. So tomorrow we're gonna have some writing. Tomorrow is, yeah. Tomorrow is the morning. In the morning we put some, yeah.